The universe is a place of profound mystery. It is filled with questions that challenge our imagination. These questions speak to the forces governing everything, from the smallest particles to the largest galaxies. One of the most thrilling quests in modern physics is the search for new forces beyond the four we already know. These are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. For decades, this idea has captivated researchers. How could new forces reshape our understanding of reality? Could they operate on scales we have yet to comprehend? Some scientists imagine a fifth fundamental force. Perhaps it is linked to dark matter or dark energy. Such a force could explain the universe's accelerating expansion. This search often leads to high-energy particle collisions. At the Large Hadron Collider, particles are smashed together at incredible speeds. These collisions create conditions similar to those after the Big Bang. They might reveal new particles or interactions. These discoveries could hint at additional forces. As we explore this potential, we also consider gravity. Could our current theories of gravity be incomplete? Modifications could explain anomalies in galaxy rotations. They might even lead to a unified theory of everything. Such a theory would reconcile general relativity with quantum mechanics. It would radically change our view of how forces interact. It would transform how we see the cosmos take shape. Researchers also investigate the role of symmetry in nature. Symmetry plays a crucial part in governing the known forces. Exploring these symmetries could unlock paths to new interactions. Then there is the possibility of forces from other dimensions beyond our familiar three-dimensional space. String theory, for instance, posits their existence. These extra dimensions could harbor unique forces. These forces would impact the interactions we observe. This idea challenges our conventional understanding of the universe. It invites us to think beyond our current scientific models. The concept of time itself could be intertwined with new forces. Some theories suggest time may not be a constant. It could be influenced by forces at a deeper, more fundamental level. This speculation raises questions about causality itself. It forces us to ask about the very nature of reality. As we delve into the quantum realm, particles behave strangely. Their behavior suggests forces we cannot yet comprehend. Quantum entanglement, for example, hints at a hidden layer of connection. Humanity's fascination with the cosmos is ancient. It has driven exploration, science, and philosophy for millennia. Ancient civilizations looked to the night sky with wonder. The Babylonians and Egyptians used the stars for navigation. They used them for agriculture and for their religious beliefs. They laid the groundwork for the astronomy we know today. The ancient Greeks also contributed significantly. Philosophers like Aristotle and Ptolemy proposed models of the universe. These models, while ultimately incorrect, sparked further inquiry. They ignited a debate about the nature of celestial bodies. The Middle Ages saw a blend of ancient and Islamic scholarship. Astronomers like al-Khwarizmi and al-Battani preserved Greek texts. They expanded upon them with new numerical methods and observations. Their work would later influence the European Renaissance. The Copernican revolution in the 16th century was a pivotal shift. Nicolaus Copernicus proposed a heliocentric model. He placed the sun at the center, not the Earth. This challenged long-held beliefs about our place in the cosmos. It ignited a scientific revolution that continues to this day. This shift was advanced by Johannes Kepler. He formulated his laws of planetary motion. He demonstrated that planets move in elliptical orbits, not perfect circles. Then came Isaac Newton's law of universal gravitation. It explained the forces governing celestial bodies with mathematical precision. The invention of the telescope in the early 17th century changed everything. Figures like Galileo Galilei made unprecedented observations. He saw moons orbiting Jupiter and the phases of Venus. This provided concrete evidence supporting the heliocentric model. As centuries passed, technology and math refined our understanding. 19th century physicists like James Clerk Maxwell developed new theories. He unified electricity, magnetism, and light into a single force. Albert Einstein's theory of relativity revolutionized our perception of reality. In the early 20th century, he changed our view of space, time, and gravity. He revealed a universe far more complex and interconnected than ever imagined. This era also saw the birth of quantum mechanics. It introduced the idea that particles at the smallest scales behave strangely. Their actions do not align with the laws of classical physics. This prompted deeper inquiries into the fundamental nature of reality. The launch of Sputnik, the first artificial satellite, was in 1957. It marked the beginning of the space age. It allowed for new perspectives of Earth and the cosmos. This led to the exploration of the Moon, Mars, and beyond. Missions like Apollo 11 brought humans to another world. In the realm of physics, 4 forces govern the universe. Each force plays a crucial role in the behavior of matter and energy. Understanding them is essential to grasping the workings of the cosmos. The first force is gravity. It seems weak compared to the others, but its range is infinite, and it is always attractive. Gravity governs the motion of planets, stars, and galaxies. It even bends the path of light, pulling objects toward one another. It is described by Einstein's general theory of relativity. This theory reveals how mass curves space-time. This curvature is what we perceive as gravitational attraction. Gravity is the grand architect of the cosmic structure. It pulls together gas clouds to form the first stars. It gathers stars into the swirling disks of galaxies. It clusters those galaxies into immense superclusters. Without gravity, the universe would be a thin, uniform soup of particles. It would be a cosmos devoid of structure of planets of life. The second force is electromagnetism. It is a much stronger force than gravity. It acts between particles that carry an electric charge. This force is responsible for electricity, magnetism, and light. It governs a vast array of phenomena, from the behavior of atoms and molecules to the formation of chemical bonds. It is described by the theory of quantum electrodynamics. This theory explains how charged particles interact by exchanging photons. Electromagnetism is the force of chemistry and biology. It holds electrons in their orbits around atomic nuclei. It allows atoms to bond together to form molecules. It is the reason solid objects do not pass through one another. Every sight, every sound, every touch is mediated by this force. The third force is the weak nuclear force. It is responsible for processes such as beta decay. This is a type of radioactive decay in unstable atomic nuclei. This force operates at very short ranges, a range on the order of a fraction of a proton's diameter. It plays a critical role in the nuclear processes that power the sunday. It enables the fusion that creates light and heat. Without the weak force, stars would not shine. The elements heavier than hydrogen would never have been created. The universe would be a cold, dark place. Finally, the fourth fundamental force is the strong nuclear force. It is the strongest of all forces, yet it operates at an incredibly short range, less than the diameter of an atomic nucleus. This force binds protons and neutrons together within the nucleus. It overcomes the intense electromagnetic repulsion between positively charged protons. It is described by the theory of quantum chromodynamics. This theory explains the interactions of quarks and gluons. The strong force is the glue that holds the material world together. Without it, atomic nuclei would fly apart instantly. Matter as we know it could not exist. Each of these 4 forces has unique properties and interactions. Advanced theories attempt to unify them. Frameworks like string theory seek to explain the fundamental nature of reality. They explore how these forces might be connected at extremely high energies. Understanding these forces helps us comprehend the structure of matter. It also allows us to explore the vast mysteries of the universe. From the smallest particles to the largest cosmic structures, discoveries in physics have profoundly shaped this understanding. Sir Isaac Newton's groundbreaking work began in the 17th century. He formulated the laws of motion and universal gravitation. He introduced the idea that every mass exerts a force on every other mass. This was a revolutionary concept. It provided a mathematical description of gravity. It allowed us to comprehend the motion of objects on Earth. It also explained the orbits of planets and moons. Newton's work set the foundation for classical mechanics. His ideas dominated our understanding of physics for centuries. They were solidified by experiments from Galileo. Galileo studied the motion of falling bodies. He demonstrated that objects fall at the same rate, regardless of their mass. This reinforced the universal principles of gravity. Fast forward to the 19th century, we encounter James Clerk Maxwell. His formulation of electromagnetic theory brought together electricity and magnetism. He revealed they are interconnected aspects of a single force. This unification led to the understanding that light is an electromagnetic wave. It fundamentally altered our comprehension of energy. It changed how we saw energy propagating through space. Maxwell's equations laid the groundwork for modern technologies. Radio, television, and wireless communication all stem from his work. It showed how theoretical physics can lead to practical applications. In the early 20th century, Albert Einstein introduced relativity. His theory fundamentally changed our perception of space and time. His famous equation reveals the profound relationship between mass and energy. It suggests that mass can be converted into energy and vice versa. This principle is not just theoretical, it has practical implications in nuclear reactions. Tiny amounts of mass yield vast amounts of energy. Einstein's work also led to a new understanding of gravity. He saw gravity as the curvature of space-time. This was a radical shift from Newton's view of an invisible force. It has been confirmed by numerous experiments, including the observation of gravitational waves detected a century later. In the mid-20th century, quantum mechanics introduced new complexity. Physicists like Niels Bohr and Werner Heisenberg explored particle behavior. They studied the atomic and subatomic levels. Quantum theory revealed a world of probabilities and uncertainties. Particles can exist in multiple states simultaneously. This leads to phenomena like superposition and entanglement. These concepts challenge our classical intuitions about reality. The formulation of these four forces was shaped by many brilliant scientists. Each brought unique insights that helped us understand the universe. Starting with gravity, Isaac Newton laid the groundwork. His law of universal gravitation described how masses attract one another. It provided a mathematical framework for the motion of celestial bodies. But it was Albert Einstein who revolutionized our understanding. His general theory of relativity proposed gravity is not a force. He said it is a curvature of space-time caused by mass and energy. Moving to electromagnetism, we must mention James Clerk Maxwell. His set of equations unified electricity and magnetism into a single theory. He showed how electric and magnetic fields interact and propagate as waves. Later, the work of Richard Feynman and others developed quantum electrodynamics. This explained how light and matter interact on a quantum level. It expanded our understanding of electromagnetic forces. In the realm of nuclear forces, the weak force was explored by Enrico Fermi. He developed the Fermi theory of beta decay in the 1930s. His contributions were crucial in understanding how subatomic particles interact. Later, Steven Weinberg and Abdus Salam developed the electroweak theory. They unified the weak nuclear force and electromagnetism into a single framework. This showed how the two are interconnected at high energy levels. The strong nuclear force was advanced by the work of Hideki Yukawa. He proposed the concept of mesons as force-carrying particles. This idea was pivotal in understanding interactions at small distances. It laid the foundation for quantum chromodynamics, a more complete theory that describes the strong interaction. This theory was refined by many others. David Gross, Frank Wilczek, and H. David Politzer were awarded the Nobel Prize. Their work solidified our modern understanding of the strong force. The development of quantum mechanics had a profound impact. It revolutionized the way we perceive interactions at the most fundamental levels. Before quantum mechanics, classical physics dominated. Its deterministic view provided a solid foundation. But scientists exploring the atomic scale found classical laws were inadequate. This led to the birth of quantum mechanics. It introduced a probabilistic nature to physical phenomena. One of its most significant contributions is its explanation of the electromagnetic force. Quantum electrodynamics describes how light and matter interact. It reveals that particles like electrons exchange virtual photons. This exchange facilitates electromagnetic interactions. This understanding has practical applications. It led to the development of lasers and semiconductor technology. Quantum mechanics also reshaped our understanding of the nuclear forces. The strong force binds protons and neutrons together. The weak force is responsible for processes like beta decay. Through quantum field theory, scientists described these forces. They are described in terms of particle exchanges. Gluons for the strong force W and Z, bosons for the weak force. This particle exchange concept allowed for a unified model. It explains how these forces operate on a fundamental level. It provides a clearer picture of matter in extreme conditions, like those found inside stars or in particle accelerators. The development of quantum mechanics has also led to the exploration of gravity. A complete quantum theory of gravity remains elusive, but researchers have ventured into theories like string theory and loop quantum gravity. They attempt to reconcile general relativity with quantum mechanics. These efforts could unveil new insights into how gravity operates, especially at the smallest scales. This might lead to a deeper understanding of black holes and perhaps the very fabric of space-time itself. Quantum mechanics also introduced concepts like entanglement. Entanglement challenges our traditional notions of locality and separability. When particles become entangled, their fates are linked. The state of one particle can instantaneously affect the state of another. This happens no matter how far apart they are. This spooky action at a distance suggests a deeper level of reality, a reality where our classical intuitions about forces and separation fail. The discovery of gravity revolutionized our understanding of space and time. Before Newton, the prevailing view was influenced by Aristotle. He suggested celestial objects moved in perfect circles. He believed they were governed by different laws than those on Earth. Newton introduced a groundbreaking, unifying concept. Every mass attracts every other mass through a force he termed gravity. This provided a mathematical framework for motion on Earth. It also extended to the movements of planets, moons, and stars. The implications of this universal law were vast. The same force that caused an apple to fall governed the orbits of the planets. This illuminated the idea that the universe operates under consistent laws. This was a significant shift from notions of separate realms. Gravity became the key to understanding how celestial bodies interacted. It led to insights into the orbits of planets and the behavior of comets. It even explained the formation of galaxies. This also laid the groundwork for Albert Einstein. He proposed that gravity is not merely a force, it is a curvature of space and time caused by massive objects. His perspective suggested that planets and stars warp the fabric of space-time. They create a sort of dip that causes other objects to move towards them. This view of gravity as a geometric property was revolutionary. It altered our perception of the universe. It allowed us to view space and time as interconnected dimensions. With this new lens, the notion of time itself changed. It was no longer a constant, unchanging backdrop. It became a dynamic entity that could stretch and warp. This leads to fascinating phenomena like time dilation. Time moves slower in stronger gravitational fields. This concept has practical implications. The Global Positioning System, or GPS, must account for these effects. It needs them to provide accurate location data. This illustrates how deeply intertwined our understanding of gravity is with our technology. Theoretical frameworks provide a structured way to understand complex phenomena. They serve as essential tools for scientists and researchers. They guide inquiries and shape interpretations of data. One of the most prominent is the theory of general relativity. It describes gravity as a curvature of the fabric of space-time. It revolutionized our understanding of how massive objects interact. In contrast, quantum mechanics offers a different perspective. It governs the behavior of particles at the smallest scales. It introduces concepts like wave-particle duality and uncertainty. These challenge our classical understanding of physics. Together, these two frameworks form the foundation of modern physics. Yet they remain fundamentally incompatible in many aspects. This prompts scientists to seek a unifying framework. String theory and loop quantum gravity are leading candidates. String theory suggests the fundamental building blocks are not particles, they are tiny vibrating strings of energy. It posits the existence of multiple hidden dimensions. These could explain some mysterious phenomena in the universe. On the other hand, loop quantum gravity attempts to quantize space-time itself. It proposes that space is composed of discrete units, much like the pixels in a digital image. This framework aims to bridge the gap between the large and the small, yet it is still a work in progress. The study of cosmology examines the large-scale structure of the universe. It uses these theoretical frameworks to interpret observation. For example, the cosmic microwave background radiation is the afterglow of the Big Bang. It provides a wealth of information about the early universe. Theoretical models help scientists understand its implications. Another aspect of these frameworks is their role in guiding experiments. Researchers develop hypotheses based on existing theories. They then design experiments or observations to test these ideas. If the results align with predictions, the theory gains support. If not, the theory may need to be revised or replaced. This iterative process of hypothesis and testing is crucial. It is how we advance our understanding of the universe. As new technologies emerge, they enable scientists to explore new realms. This leads to new theoretical frameworks and refined models. Advancements in artificial intelligence and machine learning are now helping. They assist in analyzing vast datasets from space missions. This accelerates the process of scientific discovery even further. Scientists have long recognized 4 fundamental forces, but the idea of additional forces has captured imaginations. Could there be something lurking beneath our current understanding? One prominent theory suggesting this is string theory. It posits that fundamental particles are tiny vibrating strings. In string theory, different vibrational modes correspond to different particles. This means there could be multiple hidden dimensions. In those dimensions, additional forces could exist. They could influence our universe in ways we cannot yet comprehend. Another fascinating proposal is the concept of extra dimensions. This is explored in frameworks like Kaluza-Klein theory, an early attempt to unify gravity and electromagnetism. This theory suggests that if additional spatial dimensions exist, they could host new forces. These forces might interact with the familiar 4 we know. There is also growing interest in modified gravity theories, such as MOND, or modified Newtonian dynamics. This attempts to explain galaxy rotation curves without dark matter. These theories propose that gravity itself could behave differently. It might change under certain conditions or over vast distances. This hints at a fundamental modification in how we understand gravity. It suggests a deeper connection or additional forces at play. The concept of quantum gravity also opens the door to new forces. It seeks to merge quantum mechanics with general relativity. Researchers in this field investigate how quantum fluctuations might introduce new interactions. These could potentially lead to forces that have yet to be observed. There is also a hypothesis known as the fifth force. It has surfaced in various experimental contexts. It raises questions about interactions that do not fit our existing framework. For example, some experiments have suggested anomalies in particle behavior. These could indicate the presence of a fifth force, one that would operate under specific conditions or at particular scales. This leads to exciting implications for particle physics and cosmology. Furthermore, some theories in the realm of unification are called grand unified theories. They propose that at extremely high energies, the three-gauge forces could unify. The strong, weak, and electromagnetic forces could become one. Perhaps this unification could even include additional interactions that we have yet to discover. String theory is a groundbreaking framework in theoretical physics. It proposes that the building blocks of the universe are not point-like particles. They are tiny vibrating strings. These strings can oscillate in different modes. The particular vibration of a string determines the type of particle it represents. It could be an electron, a quark, or even a graviton. The graviton is the hypothetical particle that mediates gravity. String theory seeks to unify all fundamental forces in nature. It implies that there could be additional forces at play, forces that we have yet to discover. The theory suggests our familiar forces arise from the vibrational patterns of strings, but there might be other hidden dimensions, beyond our three-dimensional perception of space and one-dimensional perception of time. In string theory, these extra dimensions could be a fertile ground for new forces. If additional dimensions are curled up in ways we cannot perceive, they could influence strings. This would lead to the emergence of new interactions not accounted for in the standard model of particle physics. The idea posits that the shape of these extra dimensions dictates how strings vibrate. This would result in new forces that could manifest under specific conditions. Furthermore, some versions of string theory, such as M theory, suggest something profound. Our universe might be just one of many, a multiverse where each universe has its own set of physical laws and forces. The implications of new forces emerging from string theory are profound. They could potentially help explain phenomena that remain puzzling, like dark matter and dark energy. These two components make up most of the universe's mass energy content, but they have yet to be fully understood. If string theory is correct, these new forces could interact with ordinary matter. They would do so in subtle ways, leading to observable effects that we have yet to measure. Researchers are actively exploring the possibility of detecting these forces. They look for them in high-energy particle collisions, like those occurring at the Large Hadron Collider. Energies there are sufficient to probe these hidden dimensions and new forces. As scientists continue to study string theory, they aim to understand the universe's structure. They also want to identify the potential signatures of these new forces. This quest for knowledge is exhilarating. It opens up a realm of possibilities where reality could be different from what we perceive. A reality where new forces might interact with the known forces in complex ways. Unification theories aim to explain how the fundamental forces are interconnected. This pursuit has profound implications for our understanding of the universe. These theories suggest that at very high energies, these forces may not be distinct. They might be different manifestations of a single underlying force. For example, in the early universe, conditions were extremely hot and dense. The distinctions between these forces might have blurred. This leads to the idea that they were all unified. This concept comes from theoretical physics, particularly string theory and grand unification theories. They propose all forces could be described by a single framework, String theory, for instance, suggests a deeper connection among the forces. It also opens the door to understanding how gravity can be reconciled with quantum mechanics. This has been a significant challenge in physics. By exploring these unification theories, scientists hope to uncover a theory of everything. This could provide insights into the very fabric of the universe, including the nature of dark matter and dark energy. Moreover, the implications extend to our understanding of the early universe, particularly during events such as the Big Bang. Energy levels were so high that the forces may have been unified. This leads to questions about the conditions that existed just after the Big Bang. How did the universe transition from that singular state to the cosmos we observe today? If we can understand how these forces behaved, then we might gain insights into cosmic inflation, the rapid expansion that occurred shortly after, and how it shaped the large-scale structure of the universe. Exploring unification theories could also impact technological advancements. Understanding fundamental forces could lead to breakthroughs in energy generation, materials science, and even quantum computing. These theories may reveal new ways to manipulate energy and matter. The quest for unification is not just about theoretical physics. It has practical implications that could transform our technological landscape. The search for unified theories is ongoing. Physicists conduct experiments at particle accelerators, such as the Large Hadron Collider. They test predictions made by these theories. Discoveries in this field could reveal a deeper, more elegant structure to our universe. Quantum gravity is a fascinating and complex area of theoretical physics. It challenges our current understanding of forces in several profound ways. Traditionally, we understand forces through two major frameworks: general relativity, which describes gravity as the curvature of space-time, and quantum mechanics, which explains the behavior of particles at the smallest scales. When we attempt to merge these two theories, we encounter significant difficulties. General relativity operates on a macroscopic scale. Quantum mechanics excels at the microscopic level. This leads to a mismatch in how we perceive and describe forces. One of the core issues is that in general relativity, gravity is not a force. Not in the traditional sense. It is the geometry of space-time itself. Objects move along paths determined by this curvature. This means gravity does not have a force-carrying particle. Unlike the other fundamental forces, electromagnetism is mediated by photons. The strong and weak nuclear forces are mediated by gluons and W and Z bosons. This absence of a graviton, the hypothetical particle of gravity, is a challenge. It makes it difficult to apply quantum principles to gravity. Moreover, at the quantum level, the concept of space-time itself becomes problematic. Quantum mechanics relies heavily on probabilities and uncertainties. As described by the Heisenberg uncertainty principle, it suggests that certain pairs of properties like position and momentum cannot both be known precisely. If we take this into account, we start to wonder about the fabric of space-time. What does it look like when viewed through a quantum lens? Some theorists propose that space-time might be discrete at the smallest scales, leading to a foamy or pixelated structure. This stands in stark contrast to the smooth continuum described by general relativity. Another challenge is related to black holes. According to general relativity, black holes are regions of space-time with immense gravity. Nothing, not even light, can escape. However, when we apply quantum mechanics to black holes, we encounter the information paradox. It raises questions about whether information that falls into a black hole is lost forever. This would violate the principle of quantum information conservation. This paradox has sparked intense debate in the physics community. It suggests that our current theories may be incomplete. The search for a consistent theory of quantum gravity drives much of modern physics. It promises not just to unify our understanding of forces, it also promises to reveal the deepest secrets of space, time, and reality itself. In particle physics, the fundamental forces govern how particles interact. These forces play a crucial role in shaping the universe as we know it. The gravitational force is the weakest of the four, but it acts over long distances. It governs the motion of planets, stars, and galaxies. It influences the structure of the universe on a grand scale. In contrast, the electromagnetic force is much stronger. It is responsible for the interactions between charged particles. It governs electricity, magnetism, and light. It plays an essential role in chemistry and the formation of matter. Moving on to the strong nuclear force. This force is the strongest of the four. It acts over extremely short ranges, binding protons and neutrons together in atomic nuclei. Without this force, atomic nuclei would not be stable. Matter as we know it would not exist. This strong force is mediated by particles called gluons. They are exchanged between quarks. Quarks are the fundamental building blocks of protons and neutrons. On the other hand, the weak nuclear force is responsible for processes like beta decay, where a neutron transforms into a proton, an electron, and an antineutrino. This force is crucial for the nuclear reactions that power stars. Including our Sun. It operates at very short ranges, similar to the strong force, but it is weaker than both the strong and electromagnetic forces. In particle physics, the relationship between these forces and particles is explored. It is done through models like the Standard Model. This model describes how forces interact with different types of particles: fermions, which make up matter, and bosons, which mediate the forces. The fundamental forces are represented by force carrier particles. Photons are the carriers of the electromagnetic force. W and Z bosons mediate the weak force. Gluons carry the strong force. Understanding these relationships helps scientists explain a range of phenomena, from the behavior of subatomic particles to the dynamics of galaxies. Research in particle physics enhances our understanding of the universe. It also informs technology and innovation. Concepts developed in this field have led to advancements in medical imaging, energy production, and material science. Observational evidence in astronomy is data collected through various means. Telescopes, space probes, and other instruments allow scientists to study the cosmos. One of the most prominent examples is the Hubble Space Telescope. It has provided breathtaking images of distant galaxies and nebulae. It has revealed details that were previously invisible to us. The light from these distant objects travels for billions of years. It allows astronomers to learn about the age and composition of the universe, and even its expansion. Another significant source of evidence is the cosmic microwave background radiation. It is essentially the afterglow of the Big Bang. It fills the universe with a faint glow detectable from any point in space. This radiation offers a snapshot of the early universe. It provides insights into its origins, structure, and evolution. The European Space Agency's Planck satellite played a key role. It measured this radiation with incredible precision. The data helps refine our understanding of cosmology. Furthermore, the observation of gravitational waves has opened a new realm. These are ripples in space-time caused by cataclysmic events, like merging black holes or neutron stars. They were detected for the first time in 2015 by the LIGO Observatory. These waves confirm predictions made by Einstein's general relativity. They provide a new way to observe the universe, allowing scientists to gather evidence about phenomena that were previously undetectable. Planetary exploration through missions like NASA's Mars rovers also contributes. They offer detailed imagery and data about the Martian surface and its atmosphere and potential for past life. This informs the search for water and life beyond Earth. Observations of exoplanets have surged in recent years. Thanks to missions like Kepler and TESS, they have revealed an astonishing variety of worlds. Some are located in the habitable zones of their stars, where conditions could be right for life. Techniques such as the transit method provide evidence of these distant worlds. This is when a planet passes in front of its star, causing a temporary dimming. It enriches our understanding of planetary systems and their formation. Additionally, the study of supernovae is crucial, especially Type 1a supernovae. They serve as standard candles for measuring cosmic distances. This allows astronomers to understand the rate of the universe's expansion. Astronomical phenomena can often hint at the existence of new forces. Scientists observe the cosmos for signs of these intriguing occurrences. One such phenomenon is the behavior of galaxies, particularly when they appear to rotate faster than expected. According to the laws of gravity, galaxies should rotate at certain speeds based on the mass of their visible matter. However, many spiral galaxies exhibit rotation curves that suggest something is missing. There is far more mass present than can be accounted for by stars, gas, and dust. This discrepancy has led to the hypothesis of dark matter. It is thought to exert gravitational influences, but its exact nature remains one of the great mysteries of modern astrophysics. Another fascinating example comes from gravitational waves. These ripples in space-time are caused by massive accelerating objects. The detection of these waves opened a new door. It allows us to understand how gravity behaves under extreme conditions. The study of gravitational waves may reveal unknown aspects of gravity. It might even suggest new forces that operate under specific circumstances. Supernovae, the explosive deaths of massive stars, are also critical. When a massive star exhausts its nuclear fuel, it may collapse under its own gravity. The light curves of these explosions describe how their brightness changes over time. They can vary greatly depending on the underlying physics. The study of these light curves can reveal new insights into the forces involved in stellar evolution and nuclear reactions, and the dynamics of matter under extreme conditions. This could potentially indicate the influence of forces beyond our current understanding. Cosmic rays are high-energy particles that travel through space. They are yet another mystery that may hint at new forces. These particles originate from sources like supernovae or active galactic nuclei. They have energies that sometimes exceed what we can produce on Earth. The mechanisms that accelerate these particles to such high energies are unknown. They could involve unknown forces or interactions, pushing the boundaries of our current physics and leading to theories that extend beyond the standard model. The cosmic microwave background radiation also offers clues. Variations in temperature and density in this ancient light can provide insights into the early universe where different forces may have reigned. Dark matter and dark energy are two of the universe's most mysterious components. They have puzzled scientists for decades, leading to intriguing questions about their nature and potential connection to undiscovered forces. Dark matter makes up about 27% of the universe. It cannot be seen directly. It does not emit, absorb, or reflect light. Its presence is inferred through its gravitational effects, like the way galaxies rotate or how light bends around massive objects. This elusive substance seems to hold galaxies together. It prevents them from flying apart due to their high rotation speeds. On the other hand, dark energy makes up about 68% of the universe. It is thought to be driving its accelerated expansion. Unlike dark matter, which exerts gravitational attraction, dark energy has a repulsive effect. It causes galaxies to move away from each other at an increasing rate. Given their mysterious properties, scientists speculate about their origins. Dark matter and dark energy might be related to undiscovered forces or particles, potentially reshaping our understanding of physics. Some researchers propose that dark matter could be linked to new types of particles, which might interact with ordinary matter in ways we have yet to understand. For example, weakly interacting massive particles or WIMPs are a leading candidate. Their discovery could point towards new physics beyond the standard model. Furthermore, the relationship between dark energy and gravity raises questions about the forces at play in the universe. Theories such as modified gravity suggest something new. What we perceive as dark energy might be an alteration in our understanding of gravity, an alteration over large distances. This could imply that there are additional forces, perhaps akin to those found in quantum physics, which have yet to be discovered. Some physicists explore the idea of a fifth, fundamental force, a force beyond the four we currently know. It could exist and play a significant role in the dynamics of dark matter and dark energy. Moreover, the search for a unified theory might reveal connections, a theory that incorporates both quantum mechanics and general relativity. String theory, for instance, posits that there are additional dimensions, which could harbor hidden forces or particles influencing dark matter and dark energy. As researchers delve deeper into cosmic observations, they hope to uncover clues that will finally solve the mystery of these dark components. In recent years, scientists have reported several intriguing anomalies in cosmic ray observations. These have led to speculation about the potential existence of new forces. Cosmic rays are high-energy particles originating from outer space. They mostly consist of protons, but can also include heavier nuclei and electrons. These particles travel across vast distances. When they collide with Earth's atmosphere, they create a cascade of secondary particles. These can be detected by ground-based observatories or satellites. One significant anomaly was observed by the Alpha Magnetic Spectrometer, a particle physics experiment mounted on the International Space Station. This experiment has detected an unexpected excess of positrons. Positrons are the antimatter counterparts of electrons. The detection of these positrons, particularly at higher energies, has sparked discussions about the possibility of new sources of cosmic rays or even new physics. Some researchers have proposed they could be evidence of dark matter interactions. Others suggest they might originate from pulsars. Pulsars are highly magnetized, rotating neutron stars. Moreover, the IceCube Neutrino Observatory at the South Pole has observed high-energy neutrinos. They seem to come from sources outside our galaxy. The nature of these neutrinos raises questions about their origins and whether they could hint at new astrophysical processes or forces at work. The detection of these neutrinos from cosmic events like supernovae is significant. It has led to the hypothesis that they could be associated with new types of particles or interactions that we have yet to fully understand. Another intriguing observation comes from the Pamela satellite. It measured cosmic ray protons and electrons and found a discrepancy in their energy ratios. This has led scientists to consider the possibility of new forces acting on these particles, or perhaps even the influence of phenomena yet to be discovered. The idea of a potential new force that could affect cosmic rays is captivating. It could reshape our understanding of fundamental physics. Additionally, the discovery of the knee in the cosmic ray spectrum is important. This is where the number of cosmic rays drops sharply at certain energies. It has led to new theories about the mechanisms that govern their propagation. Some researchers are investigating whether this knee could be a sign of unknown interactions, potentially linking cosmic rays to other areas of physics, like quantum gravity or string theory. These cosmic ray anomalies, while not yet fully understood, open the door to exciting possibilities. They challenge existing theories and push us to explore the unknown. Gravitational waves are ripples in space-time. They are caused by the acceleration of massive objects. They play a fascinating role in the quest to uncover new forces. When colossal cosmic events occur, they create disturbances that travel across the universe, stretching and squeezing space-time itself. Detectors like LIGO and Virgo are tuned to pick up these subtle waves. In doing so, they are not just observing the cosmos, they are opening a new window into the fundamental workings of the universe. This could potentially reveal new forces or interactions. As scientists analyze the data from these detections, they look for anomalies, deviations from the predictions made by general relativity. If gravitational waves exhibit unexpected behaviors, it could suggest something new. The existence of other forces or particles not accounted for in our current models. For instance, if gravitational waves show properties that differ from what we anticipate, it could be a sign of extra dimensions or even new particles that interact in ways we have yet to understand. Additionally, gravitational waves can help test theories that aim to unify the fundamental forces. Researchers are particularly interested in scenarios involving modifications to gravity, such as those proposed in theories like string theory or loop quantum gravity. These theories suggest gravity might not be the only force at play. Our understanding could be incomplete. By studying the characteristics of gravitational waves, scientists could find evidence that supports these new theories, or conversely, they could rule them out, refining our comprehension of the universe. Moreover, the echoes of gravitational waves can provide insights into the very early universe, moments after the Big Bang. During this time, different forces may have acted in ways that are no longer observable. If researchers can detect gravitational waves from this epoch, it could lead to breakthroughs in understanding how forces like electromagnetism and gravity came to be. The search for new forces through gravitational waves is still in its infancy, yet the implications are profound. As detection methods improve and as we gather more data, we may uncover new aspects of physics and perhaps even find completely new forces that govern the behavior of the cosmos. The cosmic microwave background, or CMB, is a fascinating relic. It is a relic of the early universe. Its study has opened up a treasure trove of information about our cosmos. Detected as a faint glow permeating the entire sky, the CMB is the afterglow of the Big Bang. It provides a snapshot of the universe when it was just about 380,000 years old. It allows us to peer back into a time when matter and radiation decoupled. The fluctuations in temperature and density we observe in the CMB have profound implications, not just for our understanding of the universe's origins, but also for potential new physics beyond our current models. One key way we use the CMB is through its temperature anisotropies. These are tiny variations in temperature across the sky. They reveal information about the distribution of matter and energy in the early universe. By studying these anisotropies in detail, scientists can test predictions made by inflationary models. Inflation is a theory that suggests the universe underwent a rapid expansion just after the Big Bang. The patterns we see in the CMB can either support or challenge these models. For example, certain non-Gaussian features in the data could indicate new phenomena our current understanding does not encompass, such as the presence of primordial gravitational waves or other exotic fields. Moreover, the CMB's polarization patterns provide another avenue for exploring new physics. Polarization is a result of scattering processes during the recombination era. Analyzing these patterns can help us understand the influence of dark energy and dark matter. Any unexpected deviations in the polarization data could suggest new interactions or new particles that we have yet to discover. This could lead to groundbreaking shifts in our understanding of fundamental physics. Additionally, the CMB serves as a powerful tool for exploring beyond the standard model, exploring theories such as supersymmetry or extra dimensions. These theories often make predictions about the early universe, predictions that can manifest in the CMB's properties. For instance, if certain particles predicted by supersymmetry were produced, they might leave imprints in the temperature fluctuations observed today. By comparing the CMB data with theoretical predictions, researchers can identify discrepancies that might hint at new particles or forces at play. The study of the CMB also intersects with the search for cosmic inflation's exact mechanisms, and whether that inflationary period itself was driven by forces we do not yet recognize. In the realm of space exploration, experimental approaches are crucial. They help scientists and engineers test new ideas before deploying them in real missions. One exciting area involves the use of small satellites or CubeSats. These are compact, lightweight, and cost-effective spacecraft. They can be launched in groups, allowing for distributed measurements. These satellites enable researchers to conduct experiments on the effects of microgravity, on biological organisms, materials, science, and even the behavior of fluids. This can provide insights valuable for future long-duration missions to the Moon or Mars. Additionally, researchers are experimenting with in-situ resource utilization. This refers to using materials found on other celestial bodies to support human life. For example, on the Moon, scientists are investigating extracting water ice from permanently shadowed craters. This water could be used for drinking or converted into hydrogen and oxygen for rocket fuel. This allows astronauts to produce resources locally, rather than transporting everything from Earth, which is incredibly expensive. Another fascinating experimental approach is the study of astrobiology. It seeks to understand the potential for life beyond Earth. Missions like the Mars Perseverance rover are conducting experiments designed to search for signs of past microbial life on the Martian surface. The rover is equipped with advanced instruments. They can analyze soil and rock samples looking for organic compounds. This research enhances our understanding of Mars. It also informs the search for life on exoplanets. Moreover, the advent of three-dimensional printing technology in space is revolutionizing manufacturing. With the ability to print tools, spare parts, and even habitat components, astronauts can create what they need on demand, reducing the need for large supply missions from Earth. This experimental approach is being tested on the International Space Station. Astronauts have successfully printed various items, paving the way for more sustainable practices in future space missions. Then there are the experimental technologies related to propulsion systems. Traditional chemical rockets, while effective, are limited in their efficiency. Scientists are exploring alternative propulsion methods, such as ion propulsion, which uses electric fields to accelerate ions for thrust. This offers a more efficient means of travel over long distances. In the quest to understand the universe, scientists are continually pushing boundaries. One intriguing area is the search for new fundamental forces. To explore these possibilities, innovative experimental techniques are being developed. They promise to unlock new insights into the fabric of reality. One approach involves using particle accelerators, which smash particles together at incredibly high speeds. This allows physicists to probe deeper into the subatomic world. By studying the resulting interactions, researchers can look for signs of new forces or new particles that may not fit within existing frameworks. Additionally, researchers are experimenting with ultra-sensitive detectors, designed to measure extremely faint signals. These could suggest the presence of new forces. These detectors often rely on advanced technologies, such as superconducting materials, which can detect minute changes in energy. For example, experiments at the Large Hadron Collider have used sophisticated detection methods. They search for evidence of phenomena like supersymmetry or extra dimensions. These could imply the existence of new fundamental forces. Another fascinating avenue is the use of tabletop experiments. These involve smaller-scale setups that can test the effects of hypothetical forces in a more controlled environment. These experiments often utilize precision measurement techniques, such as atomic interferometry, to detect tiny shifts in the behavior of atoms. By examining how atoms react to various stimuli, researchers can infer the influence of new forces beyond the standard model of particle physics. Moreover, experiments involving cosmic rays and astrophysical observations are also pivotal. By analyzing high-energy particles that originate from space, scientists can gather information about interactions at energies far beyond what we can achieve. This cosmic perspective can shed light on potential new forces, as these particles might interact with matter in ways that are not yet fully understood. Researchers are also tapping into the realm of quantum mechanics, exploring the peculiar behaviors of quantum systems to identify any anomalies that might suggest new forces at play. Quantum entanglement, for instance, could be a key area of investigation, as scientists look for connections between distant particles, connections that could imply new interactions or forces. Finally, collaborations across global research institutions are crucial. Sharing data and resources can lead to breakthroughs that individual labs might not achieve on their own. This collaborative spirit is essential in tackling such complex questions. Particle accelerators are fascinating devices. They play a crucial role in our understanding of fundamental forces. They contribute significantly to the exploration of forces in space. At their core, they are machines designed to accelerate charged particles, such as protons or electrons, to extremely high speeds, often approaching the speed of light. This acceleration allows scientists to create high-energy collisions, which can generate conditions similar to those in the early universe, just moments after the Big Bang. By studying the results of these collisions, researchers can gain valuable insights into the forces that hold matter together. One of the most significant contributions comes from their ability to probe fundamental particles such as quarks and leptons, the building blocks of matter. The Large Hadron Collider, for example, was instrumental in discovering the Higgs boson, a particle essential for explaining how other particles acquire mass. Understanding the Higgs boson deepens our comprehension of the Standard Model. It also provides critical information about the forces at play in the universe, including the strong and weak nuclear forces. Moreover, particle accelerators enable scientists to explore phenomena like antimatter. Antimatter is the mirror image of ordinary matter. It plays a crucial role in theoretical physics, particularly in understanding the asymmetry between matter and antimatter in the cosmos. By studying how antimatter behaves, researchers can gain insights into the fundamental forces that shape our cosmos. Additionally, particle accelerators contribute to the study of cosmic rays, high-energy particles that travel through space. By simulating cosmic ray interactions, scientists can investigate their effects and delve into the mysteries of phenomena like supernovae and black holes. This research helps to unravel the complex interplay of forces in extreme environments. Furthermore, particle accelerators are not limited to the subatomic level. They also have applications in astrophysics. For instance, they can be used to simulate conditions found in stars, providing insights into stellar formation and energy production, and the fundamental forces at work within those environments. By recreating these conditions in a controlled setting, we learn about the cosmos. The Large Hadron Collider, or LHC, plays a pivotal role in the quest to uncover new forces in the universe. It is the world's largest and most powerful particle accelerator, situated underground and built by CERN. The LHC was designed to collide particles at incredibly high energies, reaching up to 14 tera-electron volts. This allows physicists to recreate conditions similar to those just after the Big Bang. It enables scientists to probe the fundamental components of matter and the interactions between them, helping to uncover the underlying laws of physics. One key aspect of the LHC's mission is exploring the nature of the Higgs boson, discovered in 2012. This particle is important not just because it fits into the Standard Model, but also because it may point towards new physics beyond our current understanding. The Higgs boson gives mass to other particles. Understanding its properties could reveal new forces or interactions. In addition to studying the Higgs, the LHC is focused on searching for supersymmetry, a theoretical framework suggesting every known particle has a heavier partner. If supersymmetry exists, it could provide insights into dark matter, a mysterious substance that makes up about 27% of the universe. Detecting supersymmetric particles could help scientists understand the nature of dark matter and potentially reveal new forces that govern the behavior of these elusive particles. Furthermore, the LHC investigates the possibility of extra dimensions, theorized in some models of physics. If extra dimensions exist, they could provide pathways for new forces, forces we do not currently account for in our three-dimensional understanding. By smashing protons together at near-light speeds, the LHC creates varied conditions where these new phenomena might emerge, allowing physicists to search for signs of new physics, such as unusual particle decay patterns or unexpected energy distributions. As the LHC continues to operate, scientists analyze vast amounts of data. They employ sophisticated algorithms and computational techniques to sift through the information. They are looking for rare events that could indicate the presence of new phenomena and possibly new forces. The collaboration of thousands of scientists from around the world is key. Working together at the LHC represents a unique opportunity to share knowledge, resources, and expertise. Satellite experiments present an exciting frontier in the quest to understand forces in space. They enable scientists to gather data from locations far beyond Earth's atmosphere, where traditional ground-based observatories might fall short. By placing instruments in orbit, satellites can measure cosmic phenomena with unparalleled precision, capturing signals and particles that may indicate the presence of unknown forces. For instance, satellites like the Gaia mission are mapping the Milky Way with incredible accuracy. They provide insights into the distribution of dark matter. These experiments are crucial. They can reveal anomalies in the gravitational effects on celestial bodies, suggesting interactions that challenge our current understanding of physics. Moreover, satellites equipped with advanced sensors can monitor cosmic rays. By analyzing these interactions, researchers can explore the properties of fundamental forces in environments that are otherwise unreachable. The detection of unusual patterns in these cosmic rays may hint at new forces or new particles, potentially leading to groundbreaking discoveries in cosmology. In addition, experiments like the Laser Interferometer Space Antenna, or LISA, will open new avenues. LISA aims to detect gravitational waves in space. Gravitational waves are ripples in space-time. Studying them can reveal insights into the fundamental workings of gravity and the nature of space-time itself. If LISA successfully detects these waves, it could confirm aspects of Einstein's theory, but it could also expose new aspects of gravitational interactions, thereby shedding light on forces we have yet to fully comprehend. Additionally, satellite missions designed to study the cosmic microwave background provide a glimpse into the early universe, allowing scientists to investigate the forces that shaped cosmic evolution. By analyzing fluctuations in this radiation, researchers can infer the influence of various forces during the universe's infancy, potentially leading to the identification of new physics beyond the standard model. As satellites continue to evolve with cutting-edge technology, the potential expands. Innovations such as quantum sensors can measure minute changes in gravitational fields. They promise to enhance our understanding of the universe's hidden architecture. To identify signatures of new forces, scientists rely on a variety of advanced detectors. Each is designed to capture specific types of signals. One of the most prominent is the particle detector, essential in high-energy physics laboratories like the LHC. These detectors, including ATLAS and CMS, are equipped with sophisticated technology. They can track, measure, and analyze the particles produced during collisions. They utilize layers of different materials, silicon sensors, gas chambers, and calorimeters, to detect particles like electrons, muons, and jets of quarks. This can reveal the interactions of fundamental forces. In astrophysics, researchers often use telescopes with specialized detectors to observe cosmic rays and other high-energy phenomena. Ground-based observatories like the IceCube Neutrino Observatory use a unique design. A cubic kilometer of Antarctic ice is instrumented with light sensors. To detect the faint signals produced by neutrinos, neutrinos are incredibly elusive particles. The IceCube detector can help scientists search for signs of new physics, such as supersymmetry or extra dimensions. By analyzing the behavior and interactions of these neutrinos, another crucial type of detector is the gravitational wave detector. Like LIGO or Virgo, they can sense the ripples in space-time caused by massive cosmic events. These detectors use laser interferometry to measure minuscule changes in distance. These can indicate the presence of new forces or interactions. As scientists continue to explore, data from these detections may lead to groundbreaking revelations. Furthermore, scientists also depend on electromagnetic detectors, such as photomultiplier tubes and charge-coupled devices. These are critical in both optical and radio astronomy. They allow astronomers to study distant celestial objects, capturing light and other forms of electromagnetic radiation that can carry signatures of new forces, such as dark energy or modified gravity theories. By analyzing the light from supernovae or the CMB, researchers can gather clues about how these forces operate on a cosmic scale. Moreover, in cosmology, balloon-borne and satellite-based detectors measure the CMB with extraordinary precision. This allows scientists to probe the universe's earliest moments and search for the subtle imprints of new physics. The theoretical implications of space exploration are immense. They stretch our understanding of the universe, from the fundamental laws of physics to the very nature of existence itself. One of the most intriguing aspects is the concept of dark matter and dark energy. While we can observe their effects, they remain elusive, leading scientists to propose numerous theories, modified gravity and new particle interactions, all of which challenge our understanding of the universe and suggest there is much more to discover. Furthermore, the implications of quantum mechanics, particularly regarding black holes, have sparked debates around information paradoxes. Some theorists suggest that information may be lost forever in a black hole, while others argue it is preserved in some form, pushing the boundaries of our comprehension of reality and prompting questions about the fundamental laws governing the cosmos. Another area to consider is the multiverse theory. It posits that our universe may be just one of many, each with its own set of physical laws and constants. This theory, while speculative, opens up profound implications. It suggests there could be infinite variations of reality, each with different outcomes, thus challenging the very notion of what it means to be unique. The idea of parallel universes also intersects with discussions about time and space, leading to the intriguing question of whether time travel could ever be possible, and if so, what the consequences might be for causality. Moreover, the implications of discovering extraterrestrial life extend far beyond biology, touching upon philosophy, sociology, and even theology. If we were to find microbial life on Mars or intelligent civilizations elsewhere, it would be transformative. It would compel us to re-evaluate our place in the universe and our understanding of life itself. The search for extraterrestrial intelligence, or SETI, raises questions about communication, cultural exchanges, and our responsibilities, especially in light of the potential risks and benefits of engagement. Theoretical implications also arise from the study of cosmic inflation. It suggests the universe underwent a rapid expansion just after the Big Bang, leading to questions about the uniformity of the cosmos. This phenomenon challenges our understanding of the early universe. It hints at a deeper underlying structure, possibly leading to insights about the initial conditions that set the stage for everything. the discovery of a new fundamental force would profoundly reshape our understanding of the universe. It would open doorways to new realms of physics and challenge the very foundations of our current theories. Currently, we understand 4 fundamental forces. If scientists were to identify a 5th force, it would imply new interactions we have yet to comprehend, potentially uniting or further separating the known forces in ways we cannot imagine. This discovery might lead to a revision of the standard model of particle physics, which successfully describes 3 of the 4 known forces, but struggles when it comes to incorporating gravity at the quantum level. Such a revelation could provide insights into the mystery of dark matter and dark energy. These components are critical to our understanding of the cosmos, yet they remain largely elusive. A new fundamental force could help explain how dark matter interacts with visible matter, shedding light on its properties, and perhaps even revealing how it influences galaxy formation and behavior. If this new force were to interact weakly with normal matter, it might be detectable through its gravitational effects, or perhaps through new types of particle accelerators or detectors. Moreover, discovering a new fundamental force could revolutionize our understanding of the early universe, particularly during the moments just after the Big Bang. It could introduce new physics that explains why the universe evolved as it did, allowing for the formation of galaxies, stars, and planets. This new force might play a role in cosmic inflation and could lead to a deeper understanding of how the universe continues to expand today. The implications would not just be theoretical, they could also lead to practical applications, affecting technology, medicine, and energy. The understanding of fundamental forces has historically led to groundbreaking technologies, from semiconductors and lasers to advancements in medical imaging. A new force could inspire innovations we can hardly envision today. Much like electromagnetism and nuclear forces have transformed our world. Furthermore, the philosophical implications of such a discovery would be vast. It would challenge our place in the universe and provoke questions about the nature of reality itself. Are there forces or dimensions beyond our current understanding? What does this mean for the laws of physics as we know them? New forces, if discovered, could significantly reshape our understanding of how matter and energy behave in the vastness of space. Currently, we understand forces like gravity, electromagnetism, and the nuclear forces. They govern the interactions of particles and the formation of stars. However, if new forces were identified, they could lead to entirely new interactions, influencing everything from the formation of planets to the behavior of light. For instance, consider a hypothetical force that operates at very large distances, something that could alter the gravitational pull between galaxies. This new force might lead to changes in the way galaxies cluster. Instead of simply being drawn together by gravity, galaxies could experience repulsion or attraction based on this new force, causing them to behave in unexpected ways. This could result in new structures in the universe, perhaps even more complex than the filaments of galaxies we see today. Moreover, if new forces were to affect how matter interacts at the quantum level, we might see changes in the behavior of particles that make up stars. The process of nuclear fusion, which powers stars, relies on a balance of forces. A new force could alter the conditions necessary for fusion to occur, potentially leading to stars that shine in different wavelengths or have different lifespans than those we currently observe. This could influence the production of elements in the universe, affecting everything from the abundance of carbon and oxygen to heavier elements. In addition, imagine a scenario where a new force influences the fundamental constants, such as the speed of light or the strength of gravity. If these constants could vary in different regions of space, this might lead to new phenomena, where the laws of physics we take for granted no longer hold. This could change our understanding of black holes, potentially revealing new ways they interact with their surroundings. or even leading to new types of celestial objects. Furthermore, new forces might also provide insights into dark matter and dark energy. Currently, dark matter is inferred from its gravitational effects, but if a new force were tied to it, we could begin to understand its properties and its behavior more clearly. The standard model of particle physics has served as a cornerstone, but it is always subject to revision based on new discoveries. If new forces were discovered, it would almost certainly lead to a re-evaluation of the standard model. The model currently describes 3 of the 4 known fundamental forces. The introduction of a new force could imply the existence of new particles, or new interactions or mechanisms not yet accounted for. For instance, if a new force were discovered, scientists would need to explore how it interacts with existing particles. It could lead to the identification of new particles, similar to how the discovery of the Higgs boson confirmed a new mechanism. This would also raise questions about the unification of forces, an ongoing pursuit in theoretical physics. The discovery of a new force could provide insights into how these forces might unify, or it could suggest that our current understanding is incomplete. Considering the complexity of particle interactions, a new force could necessitate more, not just the addition of new particles, but also a deeper understanding of the underlying principles that govern particle physics. The implications could ripple through various fields, cosmology and astrophysics, as well as the search for dark matter and dark energy. These are 2 significant areas that already challenge the standard model. Furthermore, new forces might hint at additional dimensions or an extended framework beyond the standard model, such as string theory or other theories that attempt to incorporate gravity. Each of these scenarios would require substantial adjustments to the theoretical framework and experimental validation, perhaps even a complete overhaul of existing models. This kind of scientific evolution is not uncommon in the history of physics. Many theories once thought to be comprehensive have been modified or replaced, leading to a richer and more nuanced understanding of the universe. Thus, the possibility of discovering new forces holds immense potential to reshape our comprehension of the fundamental nature of reality, opening new avenues of research and inquiry. The laws of thermodynamics govern the principles of energy and heat transfer. They are fundamental to our understanding of the universe, but the exploration of new forces could potentially challenge or reshape these laws in ways we are only beginning to comprehend. For instance, the introduction of hypothetical forces linked to dark energy could have profound implications on how we observe energy, conservation, and entropy in cosmic events. Dark energy is believed to be responsible for the accelerated expansion of the cosmos. Understanding its nature could lead to new insights into energy dynamics on a grand scale. Some scientists suggest that if dark energy interacts with normal matter in unknown ways, it could alter things. It could alter our interpretations of the first and second laws of thermodynamics. The first law states that energy cannot be created or destroyed. It might be challenged if dark energy can somehow be converted into usable energy, leading to a scenario where energy is perceived as flowing in new ways. Moreover, the second law of thermodynamics might also face scrutiny. It posits that the total entropy or disorder of an isolated system can never decrease. In certain cosmological models, particularly those involving the multiverse, it is conceivable different regions of space could experience varying levels of entropy, potentially leading to contradictions with our established understanding. If new forces are discovered that can manipulate the flow of energy or entropy on a cosmic scale, it could mean that the universe behaves in ways that defy our current laws. Additionally, the possibility of new dimensions or exotic states of matter is intriguing. It might introduce new thermodynamic behaviors that we have yet to theorize or observe. The implications would extend beyond mere scientific curiosity. They could affect how we approach everything from energy production to understanding cosmic events. For example, the study of black holes already challenges our comprehension of thermodynamics. They seem to emit Hawking radiation, which suggests they can lose mass and energy over time, yet they still preserve the laws of thermodynamics in a broader sense. If new forces introduce additional variables into this equation, it could lead to an evolution of thermodynamic principles as we know them. Furthermore, theoretical physics is exploring concepts like quantum gravity. It attempts to reconcile general relativity and quantum mechanics. This field also examines how forces at the quantum level might influence thermodynamic laws, revealing a deeper, stranger connection between information, energy, and entropy. The potential existence of new forces in the universe opens up a treasure trove of philosophical questions. It challenges our perception of reality existence and the nature of knowledge itself. If new forces were discovered, how would this reshape our understanding of the laws of physics? Would we have to rethink the foundational principles that govern our universe? And if so, what does that mean for the concept of scientific truth? This leads to deeper inquiries about the nature of scientific progress itself. Is science a linear path to an ultimate truth, or is it a series of approximations that can be radically overturned by new discoveries? Furthermore, if these new forces interact with matter in ways we do not yet comprehend, what are the implications? What would this mean for the idea of causality? Could the introduction of new forces suggest a universe that is more interconnected and complex, more so than we have ever imagined, prompting us to reconsider our place in it? Moreover, the existence of new forces could invite questions about the limits of human understanding. Are there aspects of the universe that are inherently unknowable, or can human intellect eventually grasp all that exists? This touches on the philosophical debate of realism versus anti-realism in science. The former asserts that an objective reality exists independent of our observations. The latter suggests our understanding is shaped by our perceptions, thus potentially limiting our grasp of new forces. If these forces have effects that are not immediately observable, how do we reconcile our methods, our empirical methods of investigation, with the possibility of unseen influences? Additionally, the implications of new forces could also extend to ethics and existentialism. If new forces can manipulate matter or energy in new ways, what moral responsibilities might arise from the ability to harness such power? Would humanity be prepared to ethically engage with these forces? Or would our historical tendencies toward exploitation and dominance re-emerge? This could lead to a broader philosophical discussion about the relationship between knowledge and power, asking whether the pursuit of knowledge for its own sake is justified, especially when it may unlock capabilities that could alter life as we know it. Furthermore, the discovery of new forces could provoke thoughts about the nature of existence itself. Are these forces merely extensions of our current understanding, or do they suggest a fundamentally different layer of reality, one that challenges our definitions of space, time, and consciousness? When we think about the universe, it is easy to become overwhelmed by its vastness. The sheer scale can be mind-boggling. The observable universe is about 93 billion light-years in diameter, a distance so immense that it defies easy comprehension. 1 light-year is nearly 6 trillion miles. Imagining distances on this cosmic scale is a challenge for our minds, yet it is essential for understanding our place in the cosmos. The Milky Way galaxy alone, our home, contains 100 to 400 billion stars. It spans about 100,000 light-years across. If we were to travel at the speed of light, it would take us 100,000 years to cross our galaxy from one side to the other. Now, let us consider galaxy clusters, groups of galaxies bound together by gravity. The local group, which includes the Milky Way, is just one small part of a larger structure, known as the Laniakea supercluster. It contains about 100,000 galaxies and stretches across roughly 520 million light-years. This immense supercluster is just one of many in the universe. It highlights the interconnected nature of cosmic structures. Galaxies are not isolated, but form vast networks. Moreover, the universe is not static. It is expanding. This expansion was first observed by Edwin Hubble in the 1920s. He discovered that galaxies are moving away from us, and the farther away a galaxy is, the faster it appears to be receding. This observation led to the formulation of Hubble's law, a fundamental principle in cosmology. The concept of the expanding universe has profound implications. It suggests the universe was once concentrated in an extremely hot and dense state, often referred to as the Big Bang, which occurred approximately 13.8 billion years ago. In addition to this, the universe is governed by fundamental forces. They all play crucial roles in the formation and evolution of cosmic structures. Gravity, for instance, governs the motion of planets, stars, and galaxies, causing them to attract one another. Electromagnetism governs the interactions of charged particles, leading to the formation of atoms and molecules. The concept of dark matter arose from the mismatch between theory and observation. New forces, if discovered, could significantly alter our understanding of cosmic structures, like galaxies and clusters, by introducing interactions and dynamics that we have yet to fully comprehend. For example, the existence of new forces could lead to the formation of galaxies in new ways that differ from the gravitational mechanisms we currently understand. These forces might interact with dark matter, influencing how galaxies form and evolve over billions of years. The introduction of a new force could modify the behavior of dark matter, potentially affecting the clustering of galaxies and altering the balance between the gravitational pull of visible matter and the unseen dark matter. Moreover, if these new forces were found to operate over cosmic distances, they could reshape things. They could reshape our understanding of galaxy clusters. The dynamics within these clusters could change dramatically, as interactions between galaxies might be influenced by these forces, potentially leading to different rates of galaxy merging and interaction. This could result in a more complex evolution of clusters, where galaxies might be drawn together or pushed apart in unexpected ways, depending on the nature of the new forces involved. Additionally, such forces could play a role in the behavior of cosmic filaments. These are large-scale structures that connect galaxy clusters across the universe. These filaments are thought to be the backbone of the cosmic web. If new forces interact with the matter within these filaments, it could affect gas flows, affecting star formation in galaxies. If these forces created regions of higher pressure or density, they could trigger bursts of star formation, or on the contrary, inhibit it in different areas, leading to a more dynamic and varied cosmic landscape. Furthermore, the impact of these new forces could also extend to the large-scale structure itself. Current models of cosmic evolution rely heavily on the interplay between dark energy and gravity, but new forces might introduce additional complexities. They could influence the rate of cosmic expansion, affecting how structures grow and evolve over time. This might help to explain some observed phenomena, such as the accelerated expansion of the universe, which remains one of the great mysteries in modern cosmology. The discovery of new forces could revolutionize our understanding of how galaxies and clusters form, providing insights that challenge existing theories and models. By exploring the potential effects of these forces, we may uncover the universe's deepest secrets. In the grand tapestry of the universe, new forces could play a significant role, shaping its evolution, introducing complexities that scientists are only beginning to grasp. Currently, our understanding is framed by 4 fundamental forces. However, theoretical physicists are exploring the idea of additional forces, perhaps even forces we have yet to discover, that could influence cosmic events at various scales. One exciting area of research is the concept of dark energy. It is believed to be driving the accelerated expansion of the universe. This mysterious force, which makes up about 68% of the universe, is not fully understood. Its properties could influence the fate of galaxies, clusters, and the overall cosmic structure in ways we are just beginning to comprehend. Additionally, some scientists speculate about a fifth fundamental force, which could alter our understanding of particle interactions and cosmic evolution. If such a force exists, it could help to explain phenomena that currently baffle physicists, like the discrepancies observed in galaxy rotation curves, which suggests that some unseen mass possibly linked to dark matter is influencing their motion. Furthermore, the interplay between known and unknown forces might also be crucial in the formation of large-scale structures and in the early moments of the Big Bang. The gravitational force has been the primary driver of matter clumping together. But if additional forces come into play during these formative processes, they could lead to different outcomes in terms of the size, shape, and distribution of cosmic structures. As we delve deeper into the mysteries of the universe, the possibility of new forces could challenge our models, leading to a more nuanced understanding of the universe's past, present, and future. The integration of these new forces into our theories may help to shed light on unresolved questions, such as the nature of black holes, the behavior of matter under extreme conditions, and the enigmatic properties of dark matter. In essence, the exploration of potential new forces could act as a catalyst for a paradigm shift, prompting scientists to rethink established theories and leading to groundbreaking discoveries that reshape our understanding of the cosmic landscape. As our observational tools continue to advance, we may find the evidence we need to confirm or deny the existence of these hidden cosmic actors. The discovery of new forces in the universe could profoundly change our understanding of black holes, which have long been some of the most enigmatic objects in the cosmos. Traditionally, black holes are understood through Einstein's theory of general relativity. It describes how massive objects warp space-time, creating gravitational wells from which nothing can escape. However, the potential existence of new forces could introduce new dynamics into the behavior of black holes. For instance, if a new force were discovered, it might allow for different interactions between matter and the extreme gravitational pull of a black hole, leading to novel phenomena that we have not yet imagined. Consider how such a force could modify the way matter behaves as it approaches the event horizon. Current understanding suggests that anything crossing this threshold is irrevocably lost. But if there were a new force at play, it might influence the infall of matter, potentially allowing for some form of escape or transformation of that matter. This could lead to exciting new theories about what happens at the point of no return, challenging our existing models and assumptions. Moreover, the interplay between gravity and any newly discovered force could illuminate mysteries surrounding the information paradox, which questions how information about matter that falls into a black hole can be preserved. If new forces provide alternative pathways for information storage or transfer, it may offer solutions, suggesting that information is not lost but rather transformed or encoded in ways we are yet to fully comprehend. Additionally, new forces could also impact the formation and evolution of black holes themselves. If we imagine a scenario where these forces influence the collapse of massive stars, we might find that the conditions under which black holes form could be vastly different. This could lead to the discovery of new classes of black holes, each with unique properties that challenge our existing taxonomy, perhaps even revealing intermediate black holes or different behaviors in their spin or charge. Finally, understanding new forces could open up avenues for exploring black holes differently. If these forces interact with electromagnetic radiation or other particles in a new way, we could develop new methods to detect and study black holes, providing clearer insights into their structure and the environment around them. This could enhance our ability to observe phenomena such as gravitational waves, which are ripples in space-time caused by their mergers In the vast expanse of the universe, the fundamental forces can behave quite differently, especially in extreme environments like those found near neutron stars. Neutron stars are the remnants of massive stars that have exploded, collapsing under their own gravity to form incredibly dense objects. Their gravitational pull is so intense that it significantly alters the behavior of fundamental forces. For instance, gravity becomes extraordinarily strong in the vicinity of a neutron star. The gravitational field can be millions of times stronger than on Earth. This intense gravity affects not just the star itself, but also the space around it, warping the fabric of space-time. As a result, the usual rules of physics can seem to bend, making it a fascinating area of study. The immense gravitational forces can lead to phenomena such as gravitational waves. When two neutron stars spiral towards each other before merging, electromagnetic forces also exhibit unique behaviors in these regions. The extreme density of neutron stars creates environments where magnetic fields become incredibly strong, often reaching strengths billions of times greater than Earth's magnetic field. This leads to the creation of magnetars, a type of neutron star with an exceptionally powerful magnetic field. In such environments, charged particles are accelerated to nearly the speed of light, releasing high-energy radiation including X-rays. This intense radiation can have significant effects on the surrounding space, influencing the behavior of matter and energy in ways that are still being explored. Additionally, the weak and strong nuclear forces become highly relevant. The strong force which binds protons and neutrons together plays a crucial role in the stability of neutron stars. In fact, neutron stars are so dense they are essentially giant atomic nuclei, held together by the strong nuclear force, which is competing against gravity. The balance between these forces determines whether a neutron star remains stable or collapses into a black hole. In some regions, the interactions between fundamental forces can lead to fascinating phenomena, such as the emission of a neutron star wind, a flow of charged particles ejected from the star due to its rapid rotation and magnetic field. The behavior of forces in extreme conditions, like the Big Bang, is a fascinating subject. It combines elements of physics, cosmology, and even philosophy. To theorize about these forces, scientists rely heavily on theoretical physics, particularly the theories of general relativity and quantum mechanics. During the Big Bang, the universe was incredibly hot and dense, so much so that our current understanding of physics begins to break down. In such extreme conditions, the fundamental forces are thought to unify into a single force. This concept is part of a grand unification theory, which posits that at very high energies these distinct forces merge into one. To explore the behavior of forces during the Big Bang, physicists use mathematical models and simulations that extend the laws of physics to these extreme environments. For instance, the equations derived from general relativity are used to predict how space and time behaved when the universe was just a few moments old. However, the problem arises when trying to incorporate quantum mechanics. The Big Bang is thought to have involved quantum fluctuations, which means particles and forces behave differently than we observe today. The challenge is to create a theory of quantum gravity that can accurately describe these extreme conditions. One of the leading approaches is string theory. It suggests the fundamental building blocks of the universe are not point particles, but rather tiny vibrating strings. This theory attempts to unify all fundamental forces, including gravity, within a single framework. Researchers also look into concepts like cosmic inflation. It proposes that the universe underwent a rapid expansion just after the Big Bang, influencing how forces separated and evolved. This theory helps explain the uniformity of the cosmic microwave background radiation. Moreover, scientists study the properties of high-energy particle collisions, such as those conducted at the Large Hadron Collider, to gain insights into the behavior of particles under extreme conditions. These experiments allow physicists to recreate environments similar to those after the Big Bang, providing valuable data on how forces interact at high energies. By analyzing the results, researchers can infer how the fundamental forces might have operated during that pivotal moment in cosmic history. Theoretical physicists also explore the implications of the Higgs field, which gives mass to particles and plays a critical role in how the electroweak force separated. The technological and societal impact of space exploration is profound. It influences many aspects of our daily lives. One significant example is the development of satellite technology. It has revolutionized global communication, enabling instantaneous connections across vast distances, making it possible for us to use GPS for navigation, and providing real-time weather updates crucial for agriculture and disaster preparedness. Furthermore, satellite imagery plays an essential role in monitoring climate change, helping scientists to track environmental changes and deforestation, which ultimately informs policy decisions and raises public awareness. In addition to communication, advancements in material science have been driven by space missions. This has led to the creation of new materials that find applications in various industries. The development of lightweight, durable materials used in spacecraft has trickled down to innovations in consumer products like athletic shoes and medical devices. Space agencies like NASA have pioneered technologies such as water purification systems and advanced robotics, which have found applications on Earth, improving healthcare and enhancing safety in manufacturing. Moreover, the societal impact of space exploration fosters a sense of unity. The International Space Station serves as a testament to collaborative efforts, bringing together scientists and engineers from multiple countries, promoting peace and cooperation. This collaboration often inspires younger generations to pursue careers in STEM fields, thus driving innovation and economic growth. Furthermore, space exploration ignites curiosity, a fundamental human trait that leads to discovery. When we gaze at the stars, we are reminded of the bigger picture, encouraging us to think critically about our place in the cosmos and motivating us to protect our planet. The images of distant galaxies and the mysteries of black holes foster a sense of wonder. They keep the spirit of exploration alive. The influence of space technology extends into everyday conveniences. Weather forecasting and climate monitoring systems rely on satellite data. This technology helps us prepare for severe weather events and aids in disaster response efforts. Advancements in telecommunications driven by space missions have led to global internet access and the rise of smart technologies that shape our modern world. The discovery of new fundamental forces could lead to a revolution in technology, sparking innovations that we can only begin to imagine. For instance, consider harnessing a new force at the quantum level. This might allow for breakthroughs in quantum computing. Currently, quantum computers rely on qubits which are fragile. If a new fundamental force could stabilize these qubits, it would be a game changer. It would lead to exponentially faster and more efficient computers, capable of solving complex problems in seconds. For fields such as cryptography, drug discovery, and artificial intelligence. Moreover, imagine if a new force could influence gravity in new ways. This could open the door to advanced propulsion systems for space travel, potentially allowing us to develop spacecraft that can manipulate gravitational fields, leading to faster-than-light travel, or at least significantly reducing travel time. This would not only transform human exploration of space, but could also facilitate the colonization of other planets. In the field of energy, the discovery of a new force could yield new technologies, allowing us to tap into previously inaccessible energy sources. If we could discover a force that enables us to extract energy from the vacuum of space, we could create devices that provide unlimited clean energy. Such a breakthrough would solve the energy crisis on Earth. It would also have profound implications for powering spacecraft and habitats on other planets. Additionally, if new forces were discovered that could manipulate fundamental particles, we could see a new era in material science. Imagine materials that can change their properties on demand, becoming stronger or lighter based on need. This could lead to the development of super-strong lightweight materials for construction, aerospace, and even clothing, increasing safety and efficiency in countless applications. Furthermore, in the realm of medicine, the emergence of new forces could lead to novel therapies. If a new force could allow us to manipulate biological processes at a fundamental level, we might develop new ways to target diseases, repair damaged tissues, or regenerate organs. Such advancements could significantly extend human life and improve health outcomes, tackling diseases that are currently deemed incurable. The emergence of new forces could also influence communication technologies. If these forces could be harnessed to create new forms of data transmission, perhaps faster than light or immune to interference, it would revolutionize our globally connected society. As we look to the future of space exploration, it is fascinating to consider new forces. Both physical and technological may shape the missions that lie ahead. One of the most significant is the advancement of propulsion technologies. Ion propulsion systems, which use electricity to accelerate ions, could allow spacecraft to travel farther and faster than traditional chemical rockets. This technology has already been tested on missions like NASA's Dawn spacecraft. In the future, we could see missions that reach distant planets, or even travel to the outer edges of our solar system, in a fraction of the time it currently takes. In addition to propulsion, emerging technologies in materials science could be revolutionary. Lightweight, durable materials such as graphene are being developed, which could lead to spacecraft that are not only more efficient but also more resilient. This could mean longer missions with less risk of failure, from material fatigue or damage from micrometeoroids and radiation. Moreover, the influence of artificial intelligence and machine learning cannot be underestimated. AI can analyze vast amounts of data much faster than humans, making it invaluable for navigating space and making real-time decisions. This technology could assist in autonomous exploration, allowing rovers and probes to make decisions on their own, which is particularly important when missions are far from Earth. Another force influencing future missions is the growing collaboration between nations and private companies. The commercialization of space has opened up new avenues for exploration, as companies like SpaceX and Blue Origin develop affordable launch capabilities. This collaboration can lead to shared resources and technology exchanges, enhancing scientific research and exploration efforts. Furthermore, the exploration of new celestial bodies is a driver. Bodies such as asteroids and moons like Europa and Enceladus. These are believed to harbor essential resources, including water, ice. This could be critical for future human missions. The potential for mining asteroids for rare minerals could support space missions, and also have economic implications for Earth. The quest for sustainable life support systems in space is another emerging force. As we consider long-duration missions such as those to Mars, the need becomes crucial for closed-loop life support systems. Innovations in bioregenerative systems like growing food in space and recycling waste are key. They could make it feasible for humans to live and work in space for extended periods. Research into new fundamental forces holds exciting potential for technology on Earth. Scientists are continuously exploring the possibility of discovering additional forces or new aspects of existing forces that could change our understanding of physics and lead to revolutionary technologies. If researchers were to identify a new fundamental force, it could lead to breakthroughs in energy generation. The manipulation of such a force could help create more efficient energy systems, perhaps enabling us to harness energy in ways we have not yet imagined, potentially leading to clean and virtually limitless power sources. Moreover, advancements in understanding fundamental forces could have profound implications for material science. By comprehending how these forces interact at a fundamental level, scientists might develop new materials with unique properties, such as superconductors that operate at higher temperatures. This would revolutionize industries reliant on electrical power, such as transportation and computing. This could lead to lossless power transmission systems, drastically increasing the efficiency of our electrical grids. In addition, the exploration of new fundamental forces could enhance our communication capabilities. If researchers can manipulate force interactions at the quantum level, it might pave the way for quantum computing and quantum communication systems that are far more powerful than today's classical systems. This could result in ultra-secure communication methods, as well as significantly faster data processing speeds, transforming how we handle information. Furthermore, understanding these forces could inspire innovations in propulsion systems, particularly for space travel. If we could harness a new force, it could lead to advanced propulsion technologies, enabling faster and more efficient travel within our solar system and beyond. This could open up new frontiers for exploration, allowing humans to reach distant planets and possibly other star systems. Lastly, the study of new fundamental forces could enhance our understanding of physics itself, which often has unforeseen technological applications. Just as understanding electromagnetism led to countless technologies, a deeper comprehension of new forces could similarly lead to unexpected breakthroughs, impacting fields ranging from medicine to information technology. As researchers continue to investigate these possibilities, the implications could be vast, fostering a new era of innovation that we are only beginning to envision. Public interest in fundamental physics research could be increased through a variety of strategies. One effective approach is to enhance the visibility of research findings by making them more accessible to the general public. This could involve simplifying complex concepts and presenting them in a captivating way. Science communication initiatives like public lectures and interactive workshops can play a role. By using relatable analogies, captivating stories, and visually appealing graphics, scientists can spark curiosity and invite people to explore the mysteries of the universe. Another avenue is the integration of fundamental physics into popular culture. Films, books, and television shows often shape public perception. Collaborating with creators in these fields to portray physics in an exciting and accurate light is key. This can captivate audiences and inspire a new generation of scientists. Additionally, involving students and young people in hands-on research projects can ignite their passion. Summer camps and science fairs can provide first-hand experience in the field. Furthermore, building partnerships with schools and educational institutions can foster a culture of inquiry, where fundamental physics is taught not just as a subject, but as a way to understand the world around us. Social media also has the potential to engage a broader audience by sharing bite-sized information and behind-the-scenes looks at research and live question and answer sessions with physicists. Platforms like Twitter, Instagram, and TikTok can reach a diverse demographic, especially if the content is creative and visually engaging. Moreover, public exhibitions and science festivals can showcase cutting-edge research, allowing people to interact with scientists and ask questions, creating an environment of exploration and excitement. Engaging storytelling through blogs, podcasts, or YouTube channels can also help by explaining fundamental physics concepts in a relatable and enjoyable way, giving people an avenue to delve deeper into topics that intrigue them. Collaborating with professional organizations can help in organizing outreach programs, emphasizing the importance of physics in tackling global challenges, such as climate change and technological advancements, thus making the field feel more relevant and urgent in the public mind.